Environmental Systems and Societies for the IB Diploma Program, Pearson book, 3rd edition, Chapter 5, Land. 5.1. The guiding questions: how do soils play a role in sustaining natural systems? How are human activities affecting the stability of soil systems? 5.1.1. Soil systems. Soil forms the outermost layer of the Earth's surface and consists of weathered rock. That means rock that's been worn down by wind and rain, right? Weathered rock, organic matter, so live or dead beings, carbon-based life forms, air, and water. Okay, so soil also is composed of air and water, right? So it's weathered rock, organic matter, air, and water. Those are the 4 components of soil. Soil is a good example of an open system, as it has inputs, processes, and outputs of energy and matter. Remember from topic 1, section 1.2.5. Soil is also closely linked to other environmental systems, notably the climate and vegetative plant, right? And lithospheric, that means rocks, systems. Okay, so now you can look here at figure 5.1. You can see this soil as an open system diagram. If there is a change in one or more of the inputs, for example, climate change, there will also be a change in the soil's characteristics. So if you change climate, you're going to change the soil. Soil inputs include solar energy and heat, nutrients from weathered bedrock, sediment from upslope, moisture, and organic matter. Now we're going to look at figure 5.2, soil systems in the environment. Okay, and you can see how the slope of the land is depicted in the picture. That's important. That's not by accident. Okay. Although most diagrams of soils show them as a 2-dimensional soil profile, they are in fact 3-dimensional features and are sometimes referred to as pedons. Okay, so pedon is a diagram of a 3-dimensional diagram of soil. All right, so you can look at this picture. So you have upslope, you have woodland in this example, and evapotranspiration coming off of the vegetation there. Precipitation coming in. So precipitation is red. I mean, evapotranspiration there is red because it's an output. Precipitation is blue because it's an input. Okay, and then the water, we've got runoff there, overland flow. The rain hits the woodlands, and then it's flowing down the slope. Okay, and then it comes to an agricultural area, which could be fields on a flat terrace used for arable farming. Now, this is just an example of one slope. I mean, a diagram like this will look different depending on different locations, right? So in this imagined world, you've got these fields here. So you've got the flow coming down to the fields, and then as it slopes down further, you have flood plains and marshy vegetation. So this is the low-lying land by the rivers or by the sea, by the deltas, the coastal land. It can be coastal or it can be down by a river. Okay. And then if you look underneath that, you have the solid rock. And if you go back up the hill and look at the inputs there, you've got infiltration coming in. The water hits the trees and then follows down the roots and goes down into the soil. You do have infiltration on the fields as well. It's not shown in this picture, and it's not to the same extent. For woodland brings the water feeds the water down into the soil more easily than on fields, but it does also happen on the fields. So those are inputs. And then we've got this groundwater flow here, showing how the water moves under the rock. Okay. And so here you can see where this pedon is being taken out of and examined. So like if you were to cut a three-dimensional section, a soil like a core, and pull it out and look at it, you would see these different layers. And on the top, we would see the organic horizon. So that's where they're supposed to be the most living part of the soil, where all the organisms are, and both dead and alive, all that organic matter. And then A, you would see the mineral horizon, and then E is the alluvial or leached horizon. B is the eluvial, the deposited horizon, and C is the weathered bedrock. There are stores of weathered materials, organic matter, air, and moisture in the soil. Soil outputs include sediment, organic matter, nutrients, air, and moisture. Soils are vital resources for humans, but they can take a long time to develop. I've never thought about that. How is soil made? Fertile soil, soil that's really healthy and good for growing things. Fertile soil may be considered as a non-renewable resource due to the amount of time needed for soil development. Okay, so you can develop new soil, but it takes a really long time, which is much longer than a human lifetime. Soils are very dynamic as they are physical, chemical, and biological activities. Soils are very dynamic as there are physical, chemical, and biological activities continually taking place within them. Soils have several properties that make them useful. These include providing water, nutrients, and anchorage for vegetation in ecosystems and agricultural landscapes. What's anchorage? It means a place to hold on to, a way to stay there. An anchor is the metal, big iron thing you throw off a ship to attach to a chain and to keep the ship from going anywhere, to put it in one spot, to anchor it. Okay. Providing a habitat for decomposers, which are organisms that break down dead plant and animal matter and release that energy and nutrients into the soil. That's quite important. We'll address that more later on. This life that is in the soil, is that the soil is a habitat, a very important habitat. Okay, which have an essential role in the cycling of carbon and mineral nutrients. So that life that's in that soil, those decomposers, they're doing important stuff. Being able to act as a buffer for temperature change and for the flow of water between the atmosphere and groundwater. Okay, so you've got the atmosphere up here, right? You've got precipitation, and then down in the rocks, you have groundwater. Well, what's in between there? Soils. Their ion exchange properties, which allow them to act as a pH buffer and be able to retain nutrients and other elements against loss by leaching and volatilization. Volatilization is the loss of applied nitrogen, especially from fertilizers applied in farming to the atmosphere as ammonia gas. 5.1.2, soil composition. Soil forms the outermost layer of the Earth's surface. It contains weathered bedrock, which is called regolith, organic matter, both living and dead, air, and water. Right? It's 4 components. can look here at figure 5.3. The main components in soil. You've got your orange organic matter, your blue stripy mineral matter, which is sand, silt, and clay. You've got your green stripy water, and you've got your teal dotted air. Okay. And then it also shows chemical salts, which are plant nutrients. So the dashed line between the water store and the air store, okay, see that dashed line between the teal and the green, indicates that the proportions of these two stores are inverse to each other. Well, if you think about that, that makes sense. The water and the air in the soil are in the same place. They're between everything else. So if you have air between everything else, then you don't have water between everything else. If you have water, then you don't have air. You know what I mean? So they're going to be inversely proportioned because the air is going to exist where the water isn't, in the same space between everything else. Soil organic matter can be divided into 3 categories. Okay, so now we're looking at the living and dead stuff. Decomposing plant and animal matter called litter. Okay, so you might think about litter as in like your cat's litter box or something, but this is a different word. This is litter as in plant and animal matter that is breaking down. Okay, it's decomposing. Resistant organic matter called humus or humus. No, it's humus. It's not humus. You need a second M there for it to be a humus, I believe. Resistant organic matter called humus. Living organisms such as earthworms, springtails, bacteria, and plant roots. The bacteria are super important. So there's a lot of things. There's a lot of life in soil, and they're doing very important things. Soil microorganisms progressively decompose the plant and animal matter to produce litter, which is resistant to further decomposition. Okay, so this litter that's created by this life there that's decomposing these things, it then stays. As the organic matter is broken down, nutrients are released, especially nitrogen, phosphorus, and sulfur. In soil science, this process is known as mineralization. Okay? So this breaking down of the organic matter to get it to release these inorganic nutrients is called mineralization. Because otherwise that stuff is bound up in the organic matter. This is the way that it gets taken out of that. The average amount of organic matter in the soil is generally low at 2 to 6%, but ranges from 0.5% in semi-arid locations, so very dry places, to around 90% in peatlands. This is what peatland looks like. Soil organic matter is important because it is the main food for several soil organisms, binds mineral particles together and reduces the risk of soil erosion, improves water holding capacity. Okay, so the more organic matter you have, the more water the soil can hold. Improves porosity and aeration, so it also can hold more air, and aids the growth of plants. It is a major source of nutrients and improves soil fertility. Okay, and all these things kind of go into each other. Soil pores are spaces in the soil that are filled with air and or water. So that's what I was talking about, these in-between places, right? They're called soil pores. Macropores are large pore spaces, whereas micropores are small spaces. Micropores are often filled with water, whereas macropores may contain both air and water. Air and water. The pore space in soil may be filled with a mixture of air and water. As the amount of water in the pores increases, the amount of air in the same pores decreases. Soil water. Water is essential for soils as it enables the weathering of bedrock, the horizon development due to upward and downward movement of water in the soil. This topic, section 5.1.3, and the survival of plants and animals. So we're going to get more into this in a little bit. As soil water contains dissolved organic and inorganic substances, dissolved, right? So that means it's dissolved in the water. It is scientifically known as a soil solution. But this is not solution as in a solution to a problem. This is a solution as in stuff dissolved in water. Soil solutions supply important ions known as cations and anions, so positive and negative ones, that plants need for growth and development. Soil solution also carries matter through translocation to the subsurface soil. There are three main states of water in soils, namely gravitational water, capillary water, and hygroscopic water. Okay. Let's look at figure 5.4. This is the availability of soil water for plant use. Okay, so this is highly magnified. This stuff is, we're talking about something really small here. Okay. So let's see, down here on the bottom we have soil, and showing as the soil gets increasingly wet versus it gets increasingly dry, so saturated or drought. And then how does that look when you zoom in on the soil? Okay, so when it's not too dry or not too wet, you have capillary water available for plant roots, lost by evapotranspiration. So you can see these soil particles, and you see there's capillary water around each soil particle. So this is due to the properties of water and polar bonds and whatnot. It sticks to the soil particle. Okay, so you've got kind of almost like a little shell of water around the soil particle, and then there's air between that. Okay, so you've got pore spaces filled by air. But as things get really dry, as we go more toward drought conditions, you have your soil particles, and you don't have this like thick layer of capillary water. Instead, you just have this thin film of hygroscopic water. So hygroscopic water is unavailable for plant roots, and it's always present. So you kind of always have this film of water molecules around each soil particle, but the plants can't access it. And then you have pore spaces filled with air, so it's lots of air in between instead. And if you go the other direction, to soil that's been completely saturated with water, really, really wet, okay, we call this gravitational water. So it's also unavailable for plant roots. And then it gets lost by gravity. That means it comes through, it keeps going. Like when you have a potted plant, you pour water, and it just goes through the soil and out the drainage holes down at the bottom. Okay, that's the gravitational water. It just passes through. It's not staying there. And so that's where, in those situations, all the pore spaces are filled with water. Gravitational water refers to water movement down through the soil due to gravity. The higher the permeability of the soil, the faster the gravitational water flows through the soil. Field capacity, bolded term, field capacity, occurs when all the smaller pores are filled with water and the larger pores are filled with air. So that's a good situation, right? Capillary water refers to water held by surface tension on small particles in the pore space. Capillary water can move upwards or downwards in the soil. In warm, dry areas, capillary water may be drawn up to an evaporating surface to provide water for plants and or evaporating from the soil. This capillary water moves from wetter to drier locations. Hygroscopic water refers to water that is held in a very thin layer around each individual soil particle. It is not very accessible to plants. The permanent wilting point, bolded term, occurs when plants are unable to withdraw any water tightly held by the soil. Soils with more small particles, such as clay, will hold more water than ones with larger particles, such as sand. Clay is tiny particles of soil. Sand is big particles. And there we're talking about the inorganic component of the soils. Clay has many small pores, micropores, which reduce the rate at which water passes through, but may also reduce infiltration. If you have clay, it's hard for rain to get into this soil because it's so compact. But once it's in, it tends to hold water. So like if you pour water through sand, the water goes quite fast through it, right? Whereas if you pour water onto clay, it will have a hard time passing through. In contrast, sand has much larger pores, macropores, which allow water to pass through quickly, but reduces the amount of water available for plant use. A loam soil has both micropores and macropores. It provides water in the micropores and air in the macropores. So loam, that's good for growing stuff. 5.1.3, soil profiles. Soil formation is a slow process, sometimes taking place over thousands of years. Soil horizons develop as a result of the transfer processes, translocation, transformations, addition, and removal that occur in the open system of the soil. In most soils, there is a transition where the organic components in the upper surface layer transform into more inorganic compounds in the lower horizons. So talk about that soil profile, that you have more organic material at the top, and as you go further into the earth, it becomes more and more inorganic. And here we have this big teal skills section, which is really good to familiarize yourself with it. Because it goes through soil textures, for example, like finger assessment of soil, how you can feel the difference in soil texture. You can investigate the texture with your fingers. So soil texture, the proportion of different sized materials in soil, usually sand, silt, clay. So soil texture is the size of the soil particles, right? We'll talk about clay is small, sand is bigger, silt is in between. And so you could read through how to make a soil profile, how to characterize a soil, how to know what's going on with the soil, which then tells you how much water it can hold and how likely it is to grow something, right? And so you can use a finger assessment. You can do sieving. When you sieve a soil sample, it separates. You have a stack of sieves, which are kind of like mesh filters of different sizes, and you pour your soil sample through it, and you shake it, so that your soil separates into these different size particle groups. Okay, and that then tells you what the size of your micropores would have been. What is the composition of your soil? What are the size of the macropore? Or like how many macropores versus micropores would you have had? What is the situation with the water? Like everything we just talked about with capillary water, gravitational water, all that kind of stuff. You know, if you know how your soil is composed of sand and clay and silt, then you get a better idea of these other aspects of it that have to do with water retention and quality for growing things, right? How much air can stay in it. Right, so you got sieving, sedimentation. And that's a way of like also seeing the different, you can sieve it into these parts, or you can put it in a water column and just let it settle and use gravity to separate it out, and that's called sedimentation. You can look at soil moisture content. You can investigate the soil organic matter content, how much humus is in your soil sample. You can measure the aeration, soil bulk density, and drainage. This you can't do with like a sample so much as you need to go out into the area where you're looking and put this in and measure how fast water drains through your soil. There's a good test for that. And these aren't just ways to play with soil. These are ways of assessing and measuring important things about your soil, which we're going to see are very important for soil health, which of course is then important for other things such as food security. 5.1.4, soil system inputs. Soils are open systems as there are flows of energy and matter across soil boundaries. In these systems, there are inputs, outputs, which is losses, transfers, and transformations, resulting in the formation of soil. Inputs include heat, water, and oxygen from the atmosphere, organic matter from plants and animal remains, and the plants and animals themselves, right? Particulates from weathering and materials deposited from wind and water. So particulates from weathering, that means like when you've got wind or water going over rock, it breaks the rock down into these little particles. And then sometimes the wind can and water can carry those particles a long way and then deposit them somewhere. The development of soil is largely the result of three sets of processes: decomposition of organic matter, weathering, and movement of water in the soil. Okay, so if you're going to make soil, you're going to need the decomposition of organic matter, you're going to need to weather some rocks, and you need to have some movement of water in the soil. So here you can see this table, soil processes divided into general and specific types and the resulting soil effects. So you have primary or general processes, the incorporation of organic matter, the weathering, and the movement of water. Those three primary processes or general processes. Then you have related secondary or specific processes. So incorporation of organic matter, more specifically, is the formation of humus and soil aggregation. Aggregation is sticking together, getting the soil to stick together. Okay. And then for weathering, what is that more specifically? We're talking about oxidation and hydration. Those are secondary processes there. And then we have movement of water, which is like leaching, the water coming out of the soil. Glaying, which is water logging, like getting clogged with water. And soil salinization. So water movement can deposit, can bring salt into the soil. Then we can look at the third column, which is the role in soil formation. Primary process of incorporation of organic matter, which leads to the formation of humus and soil aggregation. And the role in soil formation is to main agent. This is the main agents responsible for development of horizons within the soil. Okay, so the fact that you have these different layers called horizons is largely related to this aspect, the incorporation of organic matter. Okay, so for weathering, the role is accumulation of parent material. So the main soil material comes from rocks. So soil is weathered rocks, right? The mineral, the inorganic component. Okay, and then the role of movement of water is the main agents responsible for development of horizons within the soil. So that is also related to the first one, incorporation of organic matter and the movement of water. They also create these different layers. So let's look more closely at these different aspects. So let's look at incorporation of organic matter more closely. What does that mean? Okay. Dead organic matter includes plant litter, so this decomposing plant stuff, dead animal biomass, and manure. Manure is feces, animal feces or poop. The incorporation of organic matter produces a surface horizon that is rich in organic matter. Okay, this top layer, really rich organic stuff. Nevertheless, the amount, type, and distribution of incorporated organic matter varies between different soils. You can see 5.9. So there are different types of soil in different places. The grassland has the highest proportion of organic matter, 12%, found in the top 60 centimeters of the soil. For forest, and then for desert shrubland. Okay. So it shows the differences in the content and distribution of soil organic matter in the upper 1.2 meters of soil from a grassland, a forest, and a desert. So if you're just looking at 1.2 meters of soil, how much organic matter would be in each of those, right? So it would be 12% versus 3% versus 1%. Some soils, such as those in tropical rainforests, deserts, and young soils, have low organic matter content due to rapid decay and breakdown or due to limited inputs. In contrast, in cool, wet climates where waterlogging is present, organic decay is slowed, resulting in thick layers of peat or humus in the upper layers of the soil. Dead organic matter is largely found on the uppermost layer of the soil, having got there by leaf fall or litter fall. Some matter is added into the upper zone of the soil through the decay of plant roots. Millions of soil organisms, such as earthworms, insects, fungi, and other microscopic bacteria, are decomposers and break down this dead organic matter. These organisms mix the decayed organic matter with the mineral soil. The top horizon in soil is generally rich in organic matter and therefore darker in color than the lower layers. Figure 5.11 shows the three distinct layers representing the different stages of decomposition in a podzol, leached under acidic conditions. At the surface, the fresh litter contains recognizable plant remains. Below this is the partly degraded fermentation layer, where decay is active, and the plant remains are difficult to recognize. Below is the humus layer, where all the plant material has degraded. As the plant material is converted to humus, any inorganic or mineral materials, such as carbon and nitrogen, are released. Beneath the humus, the mineral organic layer, a horizon, is found. Okay, so humus should no longer look like compost. You shouldn't be able to actually see pieces of organic decaying matter anymore. It should look like chocolate cake. The type of organic matter varies with region. In temperate regions associated with deciduous forest, broadleaf trees, the organic remains are fully broken down and humified most years. Earthworms and other soil organisms mix organic matter with the minerals, forming a mull humus. In areas of heathlands, and which is kind of like, this is a heathland, and coniferous forests, these evergreen forests, where conditions are more acidic, the soil organisms are much less active. This means that there is less mixing and the organic layers within the soil are more distinct, forming an acidic moor humus. Okay. Weathering. In soil science, the term weathering can be defined as the breakdown of rocks in situ, without movement. The rocks aren't going anywhere. The weathering of bedrock provides mineral particles. You can see here in table 5.3 in the lower horizon. So primary minerals, minerals from the bedrock that are resistant to weathering, such as mica and feldspar, they are mainly present in the sand and silt factions. Secondary minerals. The products of chemical weathering are present in the clay faction. They include aluminosilicates and hydrated oxides of iron, aluminum, and manganese, which are collectively referred to as clay minerals. Mull humus has a slightly acidic pH of 5.5 to 6.5 and is associated with well-drained deciduous woodlands in lowland areas. Moor humus has a pH of 3.5 to 4.5 and is associated with coniferous forests and or upland heathlands. Acidic soils often have a thin litter layer at the surface because less mixing of organic material and mineral matter occurs due to the lack of earthworms in acidic conditions. An intermediate form, molar humus, is found in areas with a pH of 4.5 to 5.5. There are two types of weathering. Mechanical, which is physical weathering, leads to the development of smaller particles of the same rock, such as scree or pebbles or stones. In chemical weathering, a rock substance is transformed into a different and new material. An example of chemical weathering is the transformation of granite into kaolinite, also called china clay. The process of weathering is important in the early development of a soil as it provides several nutrients. The weathering of calcareous rocks tends to produce basic soils, whereas soils developed on non-calcareous rocks tend to produce acidic soils that are liable to podzolization. Just talked about what that was. Podzolization is a form of leaching under acidic conditions in which iron and aluminum are leached, that means taken out, from upper horizons and deposited into the lower horizons. So they kind of like sink. Weathering also influences soil texture, the size of individual soil particles. The weathering of sandstones and gritstones produces coarse-grained, free-draining soils. In contrast, the weathering of shales produces much finer clay-rich soils that are less well-drained. Materials can also be carried onto the soil by deposition from rivers. This mainly occurs on floodplains, where the sediment that has been carried by the water is deposited because the river's velocity, how fast it's going, is reduced when it bursts its banks. Okay, so when the river goes over the side of the bank and comes up onto the floodplain, it kind of slows down. And when water slows down, the particles can sink out of it and then be deposited. Some materials, especially fine-grained sediments, may be deposited by winds. This mainly occurs when the exposed ground is dry and in areas with limited vegetation where the wind speed can remain relatively high, and this is because it's not slowed down by the vegetation. This type of deposition favors arid and semi-arid areas, so dry places. Precipitation. Precipitation may include several solutes, so minerals that are in the water, such as calcium, nitrates, so that's other components, nutrients, chlorine, potassium, sulfates, bicarbonates of sodium and magnesium, and dissolved gases. However, there are many more minerals that are also held in minute quantities. The soil solution, which is soil moisture, is important for the transfer of nutrients to plants, as well as for the transfer of elements to the groundwater and the atmosphere. Some solutes are very soluble, such as sulfur dioxide. Some solutes are moderately soluble, such as carbon dioxide and nitrous oxide. Others, such as oxygen and methane, have low solubilities, so they don't like to be in water. Soil temperature and the movement of heat. Soil temperature has an important impact on soil organism activity. Germination of seeds, plant growth, root growth, rock weathering, soil formation, and evaporation of water. So temperature affects a lot. Soil temperature can differ from air temperature for several reasons, including incoming solar radiation and albedo, heat loss by radiation, convection, conduction, and latent heat of vaporization, thermal conductivity of the soil, the heat capacity of soil. Part of the incoming solar radiation is reflected by the surface. So the air then is getting that reflection. The air can be a different temperature then if the soil is reflecting the solar radiation. The remaining part of the solar radiation is absorbed at the soil surface and transferred to heat energy that is radiated back out. This warms the soil and the air immediately above the soil and can vaporize water. Diurnal and seasonal variations in soil temperature are reduced because vegetation intercepts part of the incoming solar radiation and part of the outgoing heat radiation from the soil. Air within the plant canopy is a poor conductor of heat, so this decreases temperature fluctuations in the soil beneath. A layer of dead organic matter, litter, and/or a layer of snow has a similar effect. For example, the temperature of soil under a mulch is much lower during a sunny day, but much higher at night than that of bare soil.